This time we're going to talk about equilibrium in weak acids. So before, we talked about how acid strength is the relative amount of dissociation of the acid. So the extent to which it ionizes from the acid form into the H3O+ and the conjugate base. We can write that as an equilibrium process. See, we've got our equilibrium arrows showing that this is a potentially reversible reaction, then that it could have significant amounts of either products or reactants. When we write the reaction with this form, where we have the acid HA plus water goes to H3O plus the conjugate base, when we write the reaction that way, then the K value, the equilibrium constant, gets a special subscript, Ka, which indicates that this is an acid. So whenever we see Ka, that means it refers to a reaction written this particular way. So we see that we can write the acid dissociation reactions, write the chemical reaction, just by knowing the Ka value. So if we take this first example, acetic acid, so CH3COOH is our HA, and we can add water per our pattern and then our equilibrium arrows, and that's going to produce H3O+ because this is an acid dissociation reaction, and the conjugate base. So that means we're just going to take away one of the H's. Now it turns out in acetic acid it's actually this H at the end that we lose, and when you take organic you'll understand more about why. But yeah, so there is our acid dissociation where we have our weak acid plus water becomes our H3O+ plus our conjugate base. Okay, let's practice again, this time with HNO2. So HNO2 reacts with water to produce H3O+ and the conjugate base. So we're going to take away an H. What do we have left? NO2 minus. Okay, and so that means that the K for that reaction, this is the reaction, that goes with Ka equals 4.6 times 10 to the minus 4. We can also do that with an amphiprotic species. We know that we have Ka, so we're going to write this as though HSO4, the hydrogen sulfate ion, is an acid. Okay, so that means we're going to add water, and are we going to produce H3O+ or OH minus? We have Ka, so we want to produce H3O+. All right, and we got to find, we've removed an H from HSO4 minus, so what's left over? SO4 2 minus. And the Ka value for that reaction is 1.2 times 10 to the minus 2. Okay, so in the last slide we wrote out the reactions, but we also had the Ka values. Which of these acids is the strongest? So the strongest acid here is going to be the one with the biggest Ka. And in this case, that's going to be C, hydrogen sulfate ion, because K has the smallest negative exponent, meaning it's the biggest number. Okay, so in the same way that we can represent the pH as being negative log of the H3O+ concentration, we can also represent the Ka as pKa, which means negative log of the Ka value. And what's handy about using pH and pKa is that it helps us to compare these numbers that would otherwise be in scientific notation. So in the same way that we said, before, if we had a number, if our Ka was something like 1.8 times 10 to the minus 5, then taking the pKa, so negative log of Ka, which is the pKa, is 4.75 if you do that math. And so what that does is it helps us to focus on this exponent and thereby easily compare with other numbers. Now, sometimes students find it confusing to think about pKa versus pH. So I want you to think of it this way. pH tells us how acidic a solution is. It tells us about the H3O plus concentration. It doesn't really tell us about what's causing that H3O plus concentration, just you have some stuff mixed up, it has this H3O plus concentration. pKa, on the other hand, because it's this fundamental equilibrium constant related to a reaction, so a particular acid, the pKa tells us about how acidic an acid is, how strong an acid is. And so we can use those numbers differently. So for example, a solution of acetic acid could have any number of pH values based on how concentrated it is, but acetic acid always has the same pKa. It turns out that the pH-pKa relationship also tells us something about the form that the acid is in. So when the pH equals the pKa, that means that the acid is 50% dissociated. In other words, we have half the HA and half the A minus. And there are some settings when we'll want to know, do we have more of the acid protonated form or more of the conjugate base form? At the pKa, when the pH equals the pKa, that means we have equal amounts, or in other words, 50% of it is in the dissociated conjugate base form. We can calculate just how much is dissociated by calculating the percent dissociation. So percent dissociation is the amount of the acid that is dissociated divided by the amount that we initially started with. So if you think about your ice table, the amount that is dissociated, HA dissociated, is going to be the initial minus the amount that you have at equilibrium. Okay, so that's the amount that is not, we're in the HA dissociated is the amount that's not in the acid form anymore. Instead, it ends up being equal to the amount that is in the conjugate base form. So if we calculate our equilibrium concentrations and we compare them to the initial concentration, we can calculate the percent that is dissociated. And like we said, when the pH equals the pKa, that means we're 50% dissociated, but we could also be more or less. Okay, so thinking about what you've just learned, which of these acids is the strongest? The strongest acid in this group is HF. And we know that because it has the smallest pKa. So if we were to write this as a Ka, it would be 10 to the negative 3.5. And so that is, if we compare all of our other options, 10 to the minus 3.5 is the biggest number because it has the smallest negative exponent. So in general, a number with a smaller pKa is going to be a stronger acid. All right, but how would we actually calculate the pH of a weak acid solution at equilibrium? Because the Ka equilibrium works the same way of any other equilibrium reaction that we've used before, we can use an ice table to set up our problem, organize the information that we have, and therefore calculate the concentration of H3O plus at equilibrium. Some special things to think about in this particular type of equilibrium problem. We can get a little bit, usually a negligible amount of H3O plus from the autoionization of water. So whenever our acid solutions are really dilute so that they're close to that 1 times 10 to the minus 7th, we might need to think about some special cases. Often we'll see that we can make the approximation that the initial concentration of the acid minus X equals the initial concentration, which means we'll be able to simplify our math. And that works because most of these Ka values are pretty small. We'll see how that works in our example. I also want you to keep in mind that the pH can tell us about the H3O plus concentration at equilibrium. So we can kind of find information about the equilibrium system, which might help us solve certain kinds of problems. So as an example, distilled white vinegar. the kind you buy at the store, is a solution of approximately 0.87 molar acetic acid, which is about 5% acetic acid by volume. Acetic acid has a Ka value of 1.8 times 10 to the minus 5. So let's calculate what we expect for the pH of a 0.87 molar solution of CH3COOH, which is the formula for acetic acid. Since we're interested in pH, that means we're going to want the negative log of the H3O plus concentration of our solution at equilibrium. If we want to know the equilibrium concentration of something, that means we should probably set up an ice table. But what reaction are we going to put at the top of our ice table? We know the pattern for Ka. Since we have a Ka, we're going to use that Ka pattern. So we're going to start with our acid form, CH3COOH, and add water to produce H3O plus and the conjugate base, which is CH3COO minus. All right, and now we can find our initial change in equilibrium amounts. So we said that initial here is 0.87 molar. That we don't care about water because it's a pure liquid. The initial concentration of H3O plus is vanishingly close to 0, but really it's 1 times 10 to the minus 7th. But that's really small, so we're going to ignore it. And that the initial concentration of acetate ion, CH3COO minus, the conjugate base, really is 0. We know that our reaction needs to proceed toward the products because we have 0 products right now, so we can't go toward reactants. So we can fill in our change values set equal to x. So then if we fill in the equilibrium columns, x, and we set up our equilibrium constant expression Ka, we see that we get x squared over 0.87 minus x equals 1.8 times 10 to the minus 5. Now, because 0.87 is really big compared to 1.8 times 10 to the minus 5, we can assume that 0.87 minus x is pretty close to 0.87, that the dissociation is going to be small compared to 0.87, so that it's not going to make a big difference. If we do that, we get x squared divided by 0.87 equals 1.8 times 10 to the minus 5. And it's a lot easier to do our math because now we just have to multiply both sides by 0.87 and take the square root to get that x equals 4.0 times 10 to the minus 3. Now, we wanted to find the pH, which we said is negative log of the H3O plus concentration. The H3O plus concentration is x. So pH will be the negative log of 4.0 times 10 to the minus 3. And if I do that, I get that the pH of the solution would be 2.4. Now that's a reasonable pH for a solution of an acid, right? It's less than 7. It's also, remember that the pH is telling us about this exponent when we take the negative log, so the pH value we get is close to 3. And we also see that this x value, if we look at this x value, we see that our assumption that 0.87 minus x really is pretty close to 0.87. Because look here, if you do 0.87 minus 4 times 10 to the minus 3, or put another way, that's 0.87 minus 0.004, then if you subtract that, you will, and then round back to two significant figures, you'll see that you still get 0.87. So we see that our assumption is valid. Now, if you do that subtraction, you find x and you find that this is not true, that you subtract and you get a different number, even just a little bit of difference, then you can go back and do it using the quadratic formula, and we'll do some practice related to that. But overall, you can see that this assumption could simplify our math. Okay, so calculating the pH of a weakly acidic solution is really just about calculating concentrations at equilibrium, and we know how to do that.